This class deals with mathematical spaces, so there'll be a quick review of this before continuing in the next section where we'll look at the Navier-Stokes equations. So a space is a set, sometimes a universe with some added particular structure and definitions. Wolfram Alpha states that the concept of a space is pretty general, an important mathematical construct. A member of a space obeys certain additional properties. Space which has been investigated and found to be of interest are usually named after one or more investigators. Their practice unfortunately leads to names which give little insight into the relevant properties of a given space. The everyday type of space familiar to most people is called Euclidean space. In Einstein's theory of special relativity, Euclidean 3-space plus time, that is what we sometimes refer to as the fourth dimension, are unified into the so-called Minkowski space. The most general type of mathematical spaces is the topological space. So we'll usually refer to these spaces by names and sometimes try and remind them of these additional properties. So they're selected mathematical objects and are treated as points, consisting of relationships between particular points. For example, points can be elements of a set, functions on another space, or subspaces of another space. For example, the Banach space is a complete space of normed vectors. Banach space, for example, is a vector of x over all scalar field k, equipped with a norm, written as this double bar with a dot with a double bar x. So a Cauchy sequence xn and x, there might be an existent element x in x. A Sobolev space, for example, is a vector space of functions equipped with a norm that is a combination of the LP norms of the functions together with its derivative, up to a point of given particular order. For example, the limit of n to infinity of xn minus x would be 0. A norm space X is a Banach space if and only if each absolutely convergent series in X converges in X. For example, the sum of n to infinity of the norm x Vn is less than infinity and implies that the sum of Vn converges in X. Space usually has many adjectives, for example, integer, rational, real, complex, to help define it. For example, linear, topological, metric, projective, measure, and non-commutative spaces. Spaces have structure and, well, not always, a set of points in space with some properties. Some of these properties could be operations like adding, cutting, measuring, intersections, unions from set theory. Proximity relationships like neighbors, closeness, convergence, and distance. Hierarchy in the structures like smooth topological. Symmetries that might preserve all the structure. And ability to tell space apart like invariance, etc. For example, the linear space or vector space is a set of vectors and it might have dilatational properties. And it might also contain the operations of compositions of vectors. For example, A and B, or B and A gives A plus B. Straight lines, planes, all these are classical operations in mechanics, which we'll look at.